Thank you for the introduction. My name is Jeffrey Salmond. I'm from the software engineering group at the University of Cambridge. And so my role as a research software engineer is to, in general, help researchers from around the university optimize their code and scale up their codes to the cluster systems that we have available. And so part of that is to look beyond what I guess you would call classic HPC in the MPI world and look towards these PGAS languages. And so today I'm going to look at Fortran 2008's Coarrays, and to my mind, looking into whether they can be used in production for large scientific codes means looking at whether they have the performance and the portability and the usability required to be useful. And so today I'm going to talk about what are Coarrays. I guess some people may be familiar already with what they are. They've been around for some time. And look at the implementations of Coarrays that are available at the moment and turn to some synthetic benchmarks so that I can compare them. And lastly, look at an actual scientific code and some of the experience I've had in porting this large and nasty scientific code to distributed memory using Fortran Coarrays. So Coarrays are kind of unique in the PGAS world in that they're the only PGAS language, I think, that is part of a language standard, whereas UPC is an extension of C into a new standard. PGAS is actually part of the Fortran 2008, the Fortran 2015 standards, and it's part of the language rather than being a library implementation like something like global arrays was. And so it looks pretty much the same as classic Fortran. When we declare a shared Coarray variable, it gains an extra set of brackets. The square brackets you can see there means that it's going to be shared across all of the different images. Image is what Coarrays was referred to as like an MPI task. And if you want to refer to some remote data, you can just do that by referring directly to an array with square brackets on the end to say, I want the data from image number 1 in this case. And that's pretty much the same as an MPI get from the point of view of the programmer, except the syntax is obviously much simpler. You don't have to calculate things like window displacements, you don't have to open and close windows or fences or any of those things. That is all handled by the runtime, and so it's somewhat less error prone in that respect. Also, things like the types that you'd be seeing in an MPI call are implicit in the language. In between putting and getting data, you need to synchronize in the same way as MPI really, and that's Coarray's sync-all statement is pretty much directly compatible with an MPI barrier. And in 2015, the first Coarray standard was in Fortran 2008, and that had this remote access part of the language. And the extension in Fortran 2015 was to add collectives. And so we can have co-sum, which is sum over all of the images, and that's pretty much the same as a MPI reduce with MPI sum as the argument. Coarrays go slightly beyond the MPI standard in this case, as we can do things like user-defined reductions, which is sort of possible in some MPI ways. And again, the syntax, because it's embedded into the language, can be made somewhat cleaner than it is with MPI, whilst still being really quite the same. There's other features of Coarrays, atomics and teams. Atomics are pretty much what you might guess, and teams means being able to split your different images, your different tasks, into groups, kind of equivalent to MPI's communicators. So currently I think there's 4 major Coarray implementations which are becoming somewhat more complete. The first G-Fortran and opencoarrays is feature complete in both Fortran 2008 and the Fortran 2015 extensions, and usefully when it comes to adding this into existing code or calling into libraries, it's also compatible with OpenMP and MPI code. You can call OpenMP libraries, it's thread safe, and you can call between Coarray code and MPI code, where your Coarray images become your MPI tasks in a fairly obvious and transparent way. The second Intel Parallel Studio is Intel's implementation, which is based on Intel's compiler and their Intel MPI, which they implemented the Fortran 2008 feature set, so the remote access to images, and then they seem to have stopped. And they haven't implemented the Fortran 2015 feature set yet. I don't know whether they're planning to or not, but it doesn't seem to have moved much in the last few years. The third, OpenUH, is a academic project rather than a sort of production compiler. OpenUH is a Fortran compiler, which I think was the first open source implementation of Coarrays, and that uses GasNet as the back-end communication layer to implement the Coarrays. And lastly is Cray, and Cray, I guess, is where these ideas came from. Coarrays probably...
And now we're good.
Okay.
Well, good to go.
All right. Let me see.
Okay. Hi guys. Hope you guys had a good coffee break and were able to see some of the posters. So let's start back. It's my pleasure to welcome Dr. Hao Wang.
Thank you.
Dr. Wang is a Senior Research Associate in the Department of Computer Science and Engineering at Virginia Tech. He received his PhD in the Institute of Computing Technology at the Chinese Academy of Sciences and completed his postdoc here at Ohio State with us. His research interests include HPC, parallel computing architecture, and big data analytics. And Dr. Wang will be presenting his talk entitled Using MPI One-Sided Communication to Accelerate Bioinformatics Applications. Let's welcome Dr. Wang.
Thanks, Harry, for the introduction. I'm good, right?
Yeah.
Yeah.
So that's the one that's
Oh, this one?
Yeah.
speakers.
Okay. Hello? Yeah. I think right now I'm good. Yeah, today I will introduce our work to use an MPI, specifically use MPI one-sided communication to accelerate our driving applications at the Virginia Tech. And firstly, I want to introduce what is type of bioinformatics we have a strong interest on. And these slides will show you guys about the next generation sequence data analysis. And usually this type of the workflow include 4 important steps. First one, they use some like the biomimetic method to get the DNA from the normal tissue or blood. And then in the second step, they use some physical and chemistry method and to fragment the DNA and then wash the DNA and amplify the DNA. And after that, they use electric engineering method and the computer science method to sequence the data, and then after that to do the data analysis on your maybe other species DNA sequence. And after the third step, you get the report about the data analysis report, and you can use this report to the clinical trials for the medical usage. And today, my talk will focus on only this step, the step 3 about the NGS data analysis. And NGS data analysis becomes very important right now, and this figure shows you the cost per genome is significantly reduced since 2008. Because after this one, the next generation sequencer and the hardware become cheaper and cheaper, and then right now the bottleneck is shift from the sequence part to the back-end data analysis part on the computer science part. And this figure is a prediction about such market. And they report in the 2024, the data analysis market is boosting and will exceed 1 billion in that year. This is just for the data analysis, not including the front-end chemistry or physical or electrical engineering, just focus on the computer science part. That will exceed 1 billion. That is a big market. And this usually such application, I mean NGS applications, exhibit the irregularity, and the irregularity usually includes three types of irregularity. First one is these applications have the irregular memory access and also have the irregular control flow. And usually, in this talk, I will focus on the irregular communication patterns. And this is our driving case. We work on the Virginia Tech, work very close to their bio institutes people, and we work on many applications. For example, the basic local alignment search tool BLAST. This is for the sequence search. This is the driving case in my talk, and this application uses heuristic algorithms to do the sequence search on the database. And this type of algorithms exhibit all of the three major irregular characteristics. And other type of applications, we have the strong interest about the short read mapping. And these applications use a compressed data structure that will make the control flow very irregular. This talk, I will introduce how to optimize the sequence search algorithms use NVR-PG2. Let's look a little bit closer about the sequence search case. And the sequence search case is one to find the similarity between a query sequence with a given sequence database. For example, we give this one as a query sequence. You can think this is you can think this is just like a string, and this is a query sequence. You need to find how similar of this input sequence with your given database. And we use the sequence search tools and to check each pair of the input with the subject sequence inside the database, and then the output is a sorted similar sequence. We not only give the sequence ID and the align information, we also give the score. When we want to use a cluster to accelerate this type of applications, we usually use MPI as our basic method. And this figure illustrates how to use MPI to do the internode parallelism. And firstly, we split the database to the subset of the database from D to the D01 or DJ. And then for a given input query sequence, we schedule the query sequence to each MPI rank process and to do the local alignment. And then we can get the local alignment result, local search result, RI0 to RIJ, this result. And then after this step, we merge and sort all local result and to get the most similar result, something like the top 500 similar sequence for this database or 1,000, depending on your parameters. In the real implementation, we're not only schedule one input sequence to an MPI process, because we want to reuse some part of the data when you start your MPI process. For example, when you load your partial of your database into the memory, you need to build the index for this part of the subject sequence, and then we really do a batch mode. We schedule a batch of the sequence to each node, and then do the local alignment, and then get the result. At the same time, we can go to the second batch and to do the computation. This is a general mode of the sequence search application, and I will show you this is MPI BLAST. This application. This application is by default is the standard tools recommended by the NCBI, National Center for Biology Information, recommended by NCBI to use this one on your MPI cluster. To use this one, this is a default behavior of the MPI BLAST. You can find we can split the database on different MPI workers, 1, 2, 3 workers, and each bar means local element time. And from this figure, we can understand both the computation time and the data size on each computer node are highly diverse. Means that it is not very easy to make the local search on each computer node equally or evenly. And look closer about this, this behavior, we can find they use a dedicated master, we call this a dedicated master, to coordinate this computation. The whole computation includes 4 major steps. Firstly, after the local search, all workers will send the metadata. Means that after your local search, you have the metadata and the real output. You send the metadata to the master, and then the master do the merge and sort about the metadata, and then this master knows how many sequences from each worker will be pushed in the output file, and then the master will choose one worker as the I/O worker, and then send back the notification for all of the workers, and then all of the workers in the step 3 will send the real data to the I/O workers, and in the final step, the I/O worker will flush this part of the data into the output file. Usually, the output file is on disk. Before we go to our design, I want to present the reason why we need to redesign such a sequence search. Because in this part of the application, I mean by default MPI application, MPI BLAST application, that works very well actually. But right now, we still have some strong reasons we need to redesign this workflow. Let's think a little bit closer about this type of application, I mean the MPI BLAST. We can find the real performance bottleneck for MPI BLAST is local search. That is compute intensive part. That usually takes a long time. And another performance bottleneck is about the disk I/O. Means that you need to push the data to the disk. That is still very heavy and expensive. But right now, we found the new trends for the sequence search requirement. And the first trend is the local search right now is much faster. Just like what I mentioned, this type of algorithm uses a heuristic algorithm. And right now, many people try to make the compute lighter. And in this talk, I will show Diamond, this tool. They claim their method can be 10 times better, I mean faster than the MPI BLAST method. And the second trend is this way. Right now we found the sequence search is not used as a single tool. And usually this tool is integrated with the other tool like the GATK, that is the NGS workflow. When integrated with the workflow, that means your sequence search result not really needed to push to the disk. You can make the data in the memory and reuse in the next stage. This is new trends. When we make the compute part faster, and when we don't need to really push the data to the disk, and currently the communication part become a new performance bottleneck. This is the reason why we need to rethink the MPI BLAST mode and redesign the sequence search tools. I will show you guys the technical part about using one-sided communications for the sequence search tool. And before we go to the details, I want to list why we use one-sided communication, not to use a two-sided communication. The most important reason to us is we want to use the one-sided communication because the one-sided communication provides the more economical express method for the irregular application. You can use that one. I mean, the concept is fit the irregular communication pattern. The second one is we want to use the one-sided communication to efficiently overlap the communication and the computation part between the different batch. The third one, just like the Dick in this morning mentioned, on the two-sided communication, we need in the MPI library, we do something like the tag matching or something else. They have the overhead, and we don't want such overhead, and we want to use a one-sided communication to avoid. The basic idea, very simple. We just want to use MPI one-sided communication, put and get, to overlap the communication and the computation. This is our major motivation. And then we don't want to use a dedicated MPI process as a coordinator for the coordinate the communication port and the disk I/O port. This is our basic idea. When when we try to implement the new sequence search tool, the challenge for us is there are three major one-sided synchronization methods. The fence, the post start complete wait method, and the lock and lock. We don't know right now. We don't know which one is better. And another one is this is application level performance optimization work, and then we need to consider many different parameters. And when we do the implementation part about the first one, we are also thinking about can we provide the auto tuning method to make the tuning part more smoothly and try to not use the brute force method to the different parameters. This figure illustrates the general idea about how to use one-sided communication. Before we start the computation part, we create the windows for the metadata, just like the light blue, and for the real data, that is for the local data, that is for in the red. We register this buffer to the NPM windows, and after each NPM process finish a batch of the local computation, they will use an NPM put interface to put the metadata to all the others. In this mode, we redundantly to transfer the metadata, but use this one we can avoid a single control MPI process to make the decision which one needed to do as an IO or something, or for the data flush. After we call the MPI put, we really use a wait function to wait the finish of the MPI put for the previous batch, not for the current batch. We'll wait the finish, just like use the MPI win fence. And after we know the previous batch put the metadata finish, we merge and sort the metadata. I mean, this part is on every rapid process. We merge and sort the metadata. And then we can use some method to select out the MPI process for the final results. In our current implementation, we implement several different mechanisms. The first one is we can try use a round robin method. That is very simple. Round robin method to select the MPI process for the final results, and then we also try to consider how many real data we need to communicate. We select out the MPI process to minimize the communication in this step. After we select a process to coordinate all of the local result, we use the MPI get to get all of the data from the MPI process. Other processes at the same time can continue their computation, I mean, for the next batch of the query to do the local search. This is why we can overlap the communication, I mean, for the real data and the computation here. This is a summary of our method. This method looks like actually very simple, and I want to figure out, we implement a different weight method in this step. We use MPI fence, we use MPI flush, we also use MPI weight, and currently we also try to use MPI test, try to overlap more batches, because right now we observed after you finish the currently batch put, MPI put, when you call the MPI weight, at that time some previous batch put metadata not really finished. We have to wait, still have to wait. Let's look at the implementation part and the optimization part. First thing I want to say, we use a double buffering mechanism for the implementation, because when we finish the currently batch computation, we need to put the metadata to the other MPI process, and this time we use one window, and at the same time we need to wait for the previous batch finish. I mean, put the metadata information finish. That one we wait for another window. That is a double buffering mechanism. And then we also implement the 3 different synchronization methods. And another optimization is like this way. When we create the MPI window and register the buffers to the window, by default, we use one window, means that we create one window and each MPI process register a buffer to the same window. The problem is, actually you can find, if the people finish the MPI put information here, if we use one window, this process still wait for the other part. In order to avoid the unnecessary wait, we change this part to the multiple window, means that we create an MPI windows and register a buffer per rank per window. This is our optimization used in this work. Let's look at our early state evaluation number. And the hardware, we use a 16 node, use Intel Sandy Bridge, and we use Mellanox Connect X3. That is, I believe that is FDR InfiniBand as a communication interconnect. And the data set, we have the 2 different sample data set, ENV-NR and NR database. The first one, I think that the one is around 2 gigabyte size, and the second one, NR, is more than 30 gigabyte. We randomly select 10,000 of sequence from the target database as a sequence, as a query sequence, and try to search this part of query sequence on these 2 database. And we partition the database. We try to partition the database evenly, means that we try to keep each partition of the database have a similar ladder. I mean, the total data size is similar. We also try to keep the length of the sequence equally distributed to all the partitions. We try to make it evenly partition. And the software part, we use Diamond as our method. Diamond is firstly introduced in the Nature paper 2015. They use a C++ thread, that is just a wrapper of a pthread method, and we extended this one with MPI, and we provide the MPI 2-sided version and the MPI 1-sided version. We compare the performance, and we use the MRPH version 2.2 as our MPI library. This is a time breakdown on the 8 computer node. You can find even we try to balance the partition, the computation time, I mean in the right part figure, and in the right part figure, the computation time not balanced. And for the left part, this is about the data size for the real output. And you can find the data size still not balanced. That depends on your input, because that is input sensitive algorithm. This is our performance number on the 8 node, and we implement all of the 3 synchronization method. Fence, the first two boys fence use a multiple window and 1 window, and when we use a PSAW and multiple window and 1 window, we use a local flush method, M window and 1 window, and then the last 2 ball is a send receive method. That's a 2-sided method. The first ball we use with a dedicated master. In this case, we still use 8 computer node, but we add one more computer node as a dedicated master. And then for this one, we kick out the dedicated master, and we use 8 computer node. Every computer node face the computation called the MPI send receive. I mean, that is blocking mode to get the metadata and do the merge and sort. In this we can find we get the best performance when we use MPI when fence with a multiple window optimization. This is the best performance we can get. And in this method, we can get to the 1.4 and 1.32 speed up over the 2-sided method respectively. And actually, I have some. We're thinking about why the MPI fence can get the best performance, because usually in the MPI library we may expect the flush method is better, because flush method inside the MPI library use a peer-to-peer method to implement this one. But the fence use a connecting mode. We think the fence may be heavier than the flush, but anti-intuition looks like the fence is better, the performance is better. This is on the 16 node, and this is our search result. Compared to the two-sided communication method, our method still, the best case can be found in the MPI one fence with multiple windows. In this one, we can keep our speed up around 1.4 times better. First observation is this one. I need to talk with MPI library people to know why the MPI fence exhibits better performance than the MPI flush. Actually, I guess this may be one reason, because right now when we do the metadata input, use the MPI put to put the MPI metadata information, we use something like the auto mode. Means each MPI process will put the data to others, over others. This is auto mode, and I'm not sure this is a reason to make the MPI fence better than the MPI flush. And the second observation is this one. We found in the Diamond application, Diamond is a P-thread version actually, and when we do the computation, we can find Diamond scale up to 10 to 12 cores. Means that you still have 4 to 6 cores. I mean, you cannot scale up to all the cores. What we're thinking about is, can we use this spare cores dedicated for the MPI communication? Then in such a case, we don't consider there any delay of the message. This we don't know right now. We can talk. Summary: this work. This work we use MPI one-sided communication to accelerate the sequence search application on the InfiniBand clusters, and our experimental results show our method can get up to 1.42 times speed up over the two-sided communication. And what we are doing right now, we are analyzing performance numbers of the different one-sided synchronization mechanisms and try to understand why the performance result looks like this one, variable performance. And we're also collecting more application performance number, because Diamond is just one type of the MPI sequence search application. We still have the MPI blast. This is a standard method. And then we have interest on the PWA, that is for the short read mapping. That still can be optimized by the one-sided application. I just received the email about the announcement about the MVP 2.3 version, just like the Professor Dick Panda mentioned in this morning. In this version, the one-sided communication, I mean RMA part, heavily improved. I have a strong interest to test this version to check about the performance change. That's all about my talk. I would like to take any question. Thank you.
Let's thank the speaker first. So are there any quick questions? Saita?
You mentioned several times that you have sometimes you have like one window per destination. What does that do to the scalability and the resources that MPI library has to allocate for the window?
You mean the data size, the size, the block size?
No, every window might take some internal resource, right?
Yes.
And you know, it may be a non-trivial resource if you're doing tagging underneath or some other offset based RMA or something like that. So then how will that scale?
Yeah. Actually, this is a good question, but I don't have answer right now. I only test about the performance number from the 2, 4, 8, 16 node. But from our performance number right now, the multiple windows still can have a better performance than one window.
Yeah. So over here, did you look at any of the just the flush local and things like that that are not as heavyweight? Like fence is still like heavyweight, right?
Yeah. Just like I said, I still a little bit short by this result, because I expect the flush is better performance than the fence, but it looks like the fence is better from our numbers. I did talk with Mika and talk with him.
Yeah, I think Mingje can clarify on like that performance difference.
Yeah, because fence should not be faster than flush, right?
Yeah, this is my interpretation accurate.
I think here, maybe, I think here we need to look at the communication pattern in the application, because this application is using some outward communication. When they are using outward, they need to flush to all the destination process. That's the same as fence. Fence means you need to flush all the other process. But if you need to do outward, the internal fence implementation is better than in the application you do the public part. If you compare outward communication, whether you use anti-outward or you implement analysis by yourself, I think that's the difference.
So just one quick comment. If indeed you are doing all-to-all, by doing multiple puts, you are actually ending up doing an all-to-all V. Like by doing an all-to-all, you may get better performance because we have better algorithms in the MPI library. I think Sayantan has a comment.
Yeah, so what I'm commenting on is that if I look at the MPIC stage 4 implementation of flush, it's just waiting on a counter to see if all my outstanding puts are complete. So in that sense, fence just adds an extra overhead because it also has a tag around.
Right.
So I mean, maybe it's an implementation issue as to what flush is doing. If flush is sending point-to-point messages, then I can see that how fence might be better. But I'm not quite sure how fence would get around that because you have a point-to-point connection that we need to send messages anyway.
Right. Right.
Maybe this is
we can take it offline. Any other questions? Adam.
I think another interesting data point would be to try like a non-blocking all-to-all here. It would be interesting to see that as another bar in your graph.
That's a really good suggestion, actually. Actually, I told the student to try to add the isolated method to check out performance number. And I would definitely add the isolated non-blocking interface to compare the performance. That's a good suggestion, actually.
Sure. Bracy had a question.
How well was the communication with double buffering?
Actually, I don't think not use double buffering cannot overlap the computing part and computing range because we use NCAP put to put the metadata to all the process. We use one window, and we wait for the previous batch. That is another window. This is double buffering case. If not use buffer, not use it.
How much time was there spent waiting?
Waiting time. Actually, I have time breakdown about this one. This shows the normal line time. And with our mechanism, you can find in this type of the data set, the computation time is close to the 60. And without this one, we can find the communication with the computation at the application level for the two-sided application. That is close to the 95. Use our method, we can reduce the total computing time to something like the 75 or 74. To be honest, we didn't highlight all the communication part right now because I think the major reason is right now I will only use two windows and check about two windows. At the most, you can hide one batch of the communicating range. Yeah, this is our program. This is what I mean. If we want to try push in this direction, I definitely want to try the NPI test, wind test. If currently the previous batch is not finished, we can continue to do the next one. Yeah, I think that is your question. We will try to do that one.
So let's thank the speaker again.
Thank you.
So it's my pleasure to introduce the next speaker, Dr. Hyun Ryu. Dr. Ryu received his bachelor's from Seoul University in South Korea and his master's and PhD from Stanford and Purdue respectively. He was with the System LSI division of the Samsung Electronics Corporation and is now with the Korea Institute of Science and Technology in South Korea. And he's one of the core developers of the 3D nanoelectronics modeling tool, NEMO, in Purdue, and now leads the Intel Parallel Computing Center in Kisti. His research interest covers modeling of advanced nanoscale devices and HPC with a focus on performance enhancements for CDE. So Dr. Yu will be presenting his talk entitled Large-Scale Electronic Structure Simulations with MVAPIT2 and on KNL processors. Let's welcome Dr. Yu.
What happened? Start this section. All right. Thanks for the very nice introduction. But to me, since that so far it seems that I'm the only one who is completely on the application side. I tried to understand all the talks so far, and I couldn't find any talk who solely talking about the performance of specific applications in detail. So today, I will briefly discuss about this nice small experience of the large-scale electronic structure simulation with MVAPIT, particularly on the Intel Nitro Landing Manicore processor. So we are building the in-house code for the large-scale electronic structure simulation. And basically, the purpose of electronic structure simulation is to find the state of electron motion in an electrostatic field created by the stationary nuclei. And it is indeed widely used in very, very many areas, like physics, chemistry, and material science, electrical engineering, and even for the mechanical engineering. And it has really huge customers in the society of computational science. So this left chart shows the service statistics in Nurse Korea, and which shows like roughly 40% of people uses like quantum simulation represented by electronic structure simulation. And the right chart again shows the service statistics in Korea's supercomputer operated by Kisti. It's again roughly 42% of people runs the quantum simulation, again represented by the electronic structure simulation. So the in-house code that we have been built basically solve two partial differential equations coupled loop. The one is the Schrödinger equation, and the other is what is called as the Poisson equation. Both equations involve very large system matrices, which is called as Hamiltonian and Poisson respectively. And the size of these matrices are exactly proportional to the number of grids in the simulation domain. So numerically, to solve the Schrödinger equations involves a normal eigenvalue problem. And the Poisson equation involves the linear system problem, AX equal B. So the question is, how large are these system matrices? And why do we need to handle these system matrices using high-performance computer? So this shows like conventional nanoscale device image. And this shows like the image of logic transistor. And this shows like the optical devices represented by a quantum dot. And although the core part of these devices is like in just a few nanometers, we need to include the surrounding materials to completely predict the quantum behaviors inside this core channel. So normally, the quantum simulation of physically realizable nanoscale materials and devices involve very, very large scale atomic system. And in terms of size, it's roughly a few tenths of nanometers. And for example, if we think about silicon box, whose dimension is roughly 30 cubic nanometer, it already contains about 1 million of atoms. And in the previous slide, I told you the system matrices that we are trying to solve, the size of the system matrices are directly proportional to the number of atoms. And because for my case, I'm using 10 bases to represent a single atom. And if I want to solve like a million atom system, that means I need to solve the 10 million by 10 million matrices, either eigenvalue or AX equal B. That's why we need to parallel computing, because those kind of large matrices cannot be handled in a single PC. So these are some development strategies that we have used. And to solve these two equations, we use domain decomposition. So let's say this is a sort of the total of the device domain, and along one direction, say x, we used like an MPI-based distributed parallelism. And each decomposes slab and allocated in a single length, then further decomposed in multiple threads. So basically, we are using the hybrid parallelization using MPI and OpenMP. And in terms of matrix decomposition, this all corresponds to the row-wise manner decomposition. So each MPI process has a chunk of rows, as you see from this picture. And each chunk of row then, again, further decomposes to use multiple threads in a row-wise. And this matrix size is what's called this tight binding Hamiltonian for the Schrödinger equation. And well, it's a little bit different from conventional finite difference method, which is based on the cubic grid, because all the semiconductor material, most of the semiconductor materials that we are familiar with, like silicon, has like a cubic grid, a zinc blend or diamond structure. So to solve the Schrödinger equation, we are using what is called the Lanczos method, which is very well-known iterative algorithm to find the eigenvalue of normal eigenvalue problem of symmetry matrices. And as you see from this shows the core of Lanczos loop. And here, what I want to say is it's very simple. What it involves the matrix vector multiplier, right? Then vector dot product. And this is just the multiplication of scalar and vector. And again, vector dot product. And again, the scalar multiplied by vector. So the major two operations that need to be parallelized is matrix vector multiplier and vector dot product. This is what I want to focus. And same for the Schrödinger, same for the Poisson equation. So we have used the conjugate gradient method. And again, the main core loop consists of roughly two major numerical operations. It's again matrix vector multiplier and vector dot product. So as you know, this vector dot product can be performed by calling the MPI reduction, right? The matrix vector multiplier can be, performed by simple parallelization, which can be easily found from textbook. But here, the issue is the matrix is sparse. So we suffer from sort of cache-miss compared to the dense matrices. So for example, if we focus on the first row block and vector multiplication, then for example, we first try to multiply this block with x0, then w x1. Then we want to go to x2, but there is no element, right? So suddenly we need to go back to the first component of vector to calculate the second row. That's why we will lose the locality of data, and we'll suffer from the huge cache miss. So basically what I want to say is, the communication pattern happens in 2 points. For the vector dot product, we have one collective communication. And for this kind of matrix vector multiplier, we need to perform the nearest neighbor communication because we assume nearest neighbor coupling in the matrix. And we have night landing. So I'm pretty sure you guys know very well about these kind of things about scaling. And this shows some performance results that we have measured in the Intel night landing processors. So we tried to solve some realistic dimension, the silicon phosphorus quantum dot, which is quite popularly researched for the material candidate for the silicon quantum computing. This device corresponds roughly 2 million by 2 million Hamiltonian matrices. and we used like 0.7210 and up to 256 cores. And we used the MBAPitch 2-2.2 and compared its performance with that measured with the Interparallel Studio 2017. So when we do not use the high bandwidth memory, the scalability is not very good, particularly when we use cores more than 32 in a single load. And when we use high bandwidth memory, the scalability becomes good. I mean, up to 64 physical cores. Here we only use the MPI process. We turned off the thread option. But as you see, MBAPitch compiler to our result. In our result, the MBAPitch compiler shows like a little bit worse communication time compared to that of Intel MPI. Well, this is not real communication time because it is measured in a single load. Maybe it's just time to access the memory, right? This shows like close-up picture of the communication time that measured with respect to the different number of MPI processor. The left picture shows like the case with no HBM, high bandwidth memory, and the right picture shows the case with high bandwidth memory. So again, it shows that the comp time for MBAPitch roughly 2 or 3 times worse than Intel compiler. And I tried to understand, well, although I'm not very familiar with the MPI compiler itself, I tried to understand where this reason is, or where this symptom is coming from. And we tried to draw the 2D map. So this shows the case where we used a total of 64 MPI rank, right? And we draw like 16 by 16 map, right? Because the node that we are using has like 64 physical core, and each core has 4 hardware threads. And we can retrieve the CPU ID, right? So by creating a 16 by 16 map, we try to see, which core is mapped to which MPI process, right? So here the black part shows the core or thread where the MPI rank is not mapped at all. And the part with color shows where actually the MPI process is mapped from 1 to 64, which means from the rank 0 to 63. And this is the result in Intel MPI when we didn't use any option. So as you know, let's say this is the quadrant 1, 2, 3, 4, 1, 2, 3, 4. So the CPU group of lowest rank is created in the first quadrant, then the next one is second quadrant, and the next one is third quadrant, and then fourth quadrant. And well, in the previous slide, I told you our application involves nearest neighbor communication, right? So in this case, the communication is quite easy, except in this point, right? So this point, communication is quite nice, but the communication between the second quadrant and third quadrant would be a little bit far in terms of memory access pattern, right? And the third and fourth is also not very bad. But for the case of MBAPitch, when we didn't use any option, well, it's completely random. So do you want to compare these two pictures? So for example, this guy and this guy, like consecutive, this guy and this guy are just MPI process, but it's quite far. So, and because I'm using quadrant mode here, that means this rank to communicate. To make the communication between this MPI process and this MPI process And this process must read their data, some memory here, and need to transfer the data, some memory here, right? Maybe my expression may not completely perfect in terms of computer science terminology, but well, hopefully it's going to make sense to you guys. So compared to this case definitely would need to communication between memory spaces quite far, which is quite far. So this shows some more case. The case of 16 MPI process and 16 MPI process with the Intel MPI and FPG2 and 64 and 64. So for example, this case, for the case of 16 MPI, the result is quite similar, right? And FPG2 shows a completely random displacement of the MPI process, right? In terms of CPU ability. And another issue maybe is the fact that they try to map multiple MPI processes in a single physical core. So in this map, these four 2x2 small box indicate a single physical core, because a single physical core has like the four hardware process. So because multiple MPI processes map a single physical core, the computational speed might hurt. So in this case, the best opportunity for this kind of workload would be like clockwise mapping of MPI process, right? But I didn't figure out how to do it as a compiler option. But it seems that the recently released MPH version now has the CPU affinity, and I really want to try it. Yeah, so how much time do I have? Yeah? Oh, really? Okay. And so maybe you guys may think this kind of things may not be a big deal because I'm sorry. Well, the communication time itself doesn't account much about the total time. But when we use multi-node, the situation is a little bit different. So the multi-node scalability is generally good. Well, this is something that has been measured in three computing nodes, and this is with high bandwidth memory and without high bandwidth memory. Right. And the computation time itself reduced very well, and the problem is communication time. And we really don't know whether this communication time comes from the network speed or intranode memory communication, or how can I say, memory transfer, which could happen due to the CPU opponent that I discussed so far. Okay. So yeah, I will definitely want to dig on more with the new version. And so this is what I have so far. Before closing my talk, I want to thank all the members of the KIST IPCC project, and thank you for listening.
Any questions? Yeah.
Quick question. Is the code available for us to try out?
If you want, I mean, it's not open, but it can be released on the condition of research collaboration.
Sure. We can definitely do that. So we are looking for codes to see exactly these kind of patterns where the communication is more, and trying to see what sort of
things we can do inside MLabs to address the scalability limitations that arise from these codes.
Okay. Sure, we can discuss later.
I think I missed a portion of your talk. Which version of MLabs 2 were you using here?
I'm sorry?
Which version of MLabs 2 were you using for this?
2.2-2.2.
Okay, thank you.
Yes.
Yeah, so I think just a comment might be Jahangir. You want to talk with him?
So I have, so can you go to that matrix of the communication?
This?
Yeah.
Yes.
These are just the MPI RAGs mapping,
Yeah.
right?
Yeah.
But you are using MPI plus OpenMP. So what I feel is that probably there is a resource contention going on when MPI, with the MPI RAGs as well as the OpenMP threads are also getting bound to the similar code. That's why. But in latest release, we have introduced some new variables for the thread affinities as well. With that, you can get a scattered mapping. With
Yeah.
And I'm pretty sure this kind of degradation will go away with that.
Okay, I'll try.
I can single
Actually, I will try. Yeah.
Yes.
And I have a quick question. Did you compare the mapping provided with the API and the one done by the I have a quick question. Did you compare the mapping of the MPI task provided with the Intel MPI and the
So this is the result of the Imperial MPI when I didn't use any option.
But I mean, on which core each MPI task were lying?
Maybe I don't understand what.
No, I think he's asking, he showed some, he's saying exactly comparing Intel MPI and MLabs 2.
Yeah, this is the
No,
result.
but in terms of which, for example, the 1.0, which core was used, 1.1, which core was used?
Oh, maybe this additional slide may be helpful for
Yeah, that.
this. So actually, there is an approximation. So there is an approximation. So, for example, as you might know, we know, for example, in one quadrant, in this quadrant, we know the core, 16 core. With 16 cores are staying in this quadrant, but frankly speaking, we don't exactly understand, for example, where is code 0 in this quadrant.
Because there is some options, like MD2 CPU binding,
Oh, really?
or IMPI debug equals 3 that will provide that information.
Okay, I didn't know that.
Because it can be useful to be sure that you are comparing the same mapping.
Okay.
to MPI library, because
Okay, so anyway, just to conclude about my approximation is although we used some approximation because so far, because I didn't know that option. So far, we really exactly didn't know, for example, where code 0 is exactly placed in this tile, in this quadrant. But the general message that I deliver would not hurt, because anyway, it's more about the communication between, how can I say, quadrant and quadrant, right? So definitely I will try that option, and maybe I need to ask one more time after this call. Thank you.
I think there's one question.
Yeah, I'll do something other than core placement, but I think you're going to get a lot of feedback that you're going to have the power to actually make both stacks do the exact same thing, and you'll get, I think, more interesting results. You're sort of seeing what happens when you don't send anything, which is an important setting for computational scientists, because you don't know necessarily what to do, but you're seeing very firsthand, particularly on a mini-core processor,
Exactly.
how important this is.
Exactly.
You didn't even talk about other thread affinities. So anyway, my question was about HBM. You talked about differences between using it and not using it, but I wasn't sure, when you say use it, do you mean you're actually allocating some portion of the internal data structures there for matrix vector multiply, or are you using it in cache mode?
Okay. Well, this result itself used like a NUMA control. That means I try to solve the whole calculation in HBM. For this case,
it's a small case there.
Relatively, but I tried like on one much larger case, and for that case, I only allocate the sparse matrix part in HBM.
I see.
And in that case, the performance was not very different from this case, which is not reported yet.
Okay.
Okay.
But you are physically allocating that.
Yeah, yeah.
Okay, thanks.
What kind of MPI operations are done here, like MPI connectives or?
Why am I confused about this option? Sorry.
This is the slide.
Yeah.
What kind of MPI operation am I doing? Well, two. roughly two MPI ODs, which is needed to perform the backwards product, and asynchronous communication. I send, I receive between the nearest neighbor to perform the matrix vector multiplier. So that's all.
So with HBM, you probably will see difference, or improvement in on-reduce. I send ITC probably not, unless it's really dense.
Maybe. Well, the other thing that I observed was like the effect of HBM was not quite, how can I say? It depends on the size of the problem, but for this size, I realized that the effect of HBM was not that great in terms of the performance improvement for the PG2 in this case. And well, there are two reasons. The first reason is what I discussed, with an example of CPU affinity, and the other one is memory bandwidth, particularly for this case, right? 32 to 64, and the wall time does not reduce at all, right? In this case, that's because like the limitation of DRAM, the memory bandwidth. Because anyway, this is large-scale sparse matrix involved operation. So this is like the memory intensive operation rather than computing intensive one. Makes sense? Okay.
Any other questions? Yeah, there's one question there.
I just have one comment about the communication comparison between the internet and RPC. So here, the underlying network, are you using TSM or IB?
I try to use both, but it does not cause a huge difference so far.
Okay, because on TSM, we see on the TSM level, they have different communication protocol.
Mm-hmm.
Because this lack of the class protocol there, I think the communication performance may come from TSM level.
Of course. But but so far I really do not exactly understand what's the reason. Here, the result is the case, how can I say? This is the result of tangent network. This is the result of tangent network. But we internally also have the OmniPath, so we also try to use that. But well, the communication time was not very different, even in multi-node case. So we're still investigating the reason. Okay.
Any other questions? Okay, so if not, let's again thank Professor Rio.
Thank you.
Okay, so that concludes all the presentations for today, and then we have the fun session.